Okay. Try this question, all of you. A simple circuit like this is given. Okay, it's not that simple, but okay, let's say a circuit like this is given. 2 ohms, assume this resistor is 1 ohm. This resistor is also 1 ohm. Let's say this battery's voltage is 10 volt and this is 20 volts. Okay. You have to find out the current in every branch of the circuit. Okay, so some batteries and some resistors are present. So tell me how you'll start solving this problem. The aim is to find out current in every branch. So how will you start the question? Start solving.
So we can divide it into 2 parts and then solve each one of them separately and add them.
So you're saying, okay, wait, this is a new idea that I heard for the first time. You're saying we'll split it into one circuit like this and another circuit like this. Is this what you're saying?
No, sir, it's like taking the no, sir, that's not. I'm so sorry.
Okay, anyway, what is your idea? Okay, Anugraha is saying we'll use KVL for different loops. Okay, that seems reasonable. But yeah, to use before using KVL, what should you consider? Or Anugraha, you tell me. Let's consider 2 loops here. Let the upper part be one loop and the lower part be another loop. How will you write KVL for the upper part? Where will you start from? Which way will you move? And tell me the voltages that you will take.
So do we have to find the net current before applying KVL?
You have to assign some currents, unknown currents you will have to assign to each branch. Okay, see the question itself is to calculate current in each branch, right? In all branches. So first assume some currents to be flowing in those branches. Now we can see 3 branches here. See, branch is effectively a part of the circuit or a straight part of the circuit which has some elements in it. Okay, like a resistor or a battery or a capacitor or an inductor, maybe combinations of those also. So we can see 3 branches here. This is 1, this is 1, and this is 1. We have to find currents in all 3. So how shall we begin? Can you tell the direction of flow of current in any branch for sure? Just by looking at the circuit, can you tell the direction of flow of current in any of the branches?
So for the bottom 2 branches, it's towards left.
How are you sure that it is towards left?
There's only resistor and batteries there, so it should be from positive terminal. Oh no, for the bottommost branch, it's towards the left.
What about the middle?
We have to calculate.
See, we cannot say. If only this 10 volt battery had been there, it will drive current this way. Okay. And some of that current will go like this and some of that current will go like this. If only the 10 volt was present. But there is a 20 volt as well. 20 volt, what it will do, it will drive current this way, some of which will flow in this branch and some of which will flow in this branch. So in the middle branch, if you see, one battery is trying to drive current to the left, the other battery is trying to drive current in it through the to the right. So we don't know what is going to be the final direction of current in that branch, and you don't need to know also. Okay, that's the advantage we have. You can assume current to be flowing in whichever direction you want. If it's actually flowing in the opposite direction, you will get a negative answer. That's all. Okay, fine. So let's begin. In the bottommost branch, let's take this. Let's take the current as I1. In the middle branch, let's take the current as I2. And in the third branch, let's take it as I3. 3 branches, 3 currents. Okay, and to calculate 3 currents, 3 unknowns, we'll need 3 equations. Yash is asking, what if the batteries were parallel? Yash, when do you say 2 batteries are in parallel? We still didn't discuss the concept, but you may be knowing that. How do you decide if 2 batteries are parallel or not? Are these 2 batteries parallel?
Sorry, sir. I wanted to say, like, what if they were in series, sir?
Okay, let us finish this question first. If they are in series, it's very easy. Okay. Anyway, combination of cells in series and parallel we'll discuss. We still didn't come to that point. Anyway, see, there are 3 unknowns. Okay, currents in 3 branches. So we'll need 3 equations. Can any of you tell me what are the 3 equations that you are going to write?
Two equations for each of the smaller loops and one for the whole big.
Okay, so you are saying we'll write 2 equations for the 2 smaller loops. Okay, I'll take one in green, one in yellow. And you are saying you will take one for the big loop like this. But see, if you write 2 equations for the smaller loops, okay, let's call this as the first equation and let's call this as the second equation. If you write equations for 1 and 2, loop means you are indirectly saying KVL, voltage law. You apply KVL for the first loop and second loop. Then you apply KVL for this outer loop. Let's call that as the third equation. You will see that the third equation is simply the sum of the first and second equation. So it's not a new equation that you are writing. And you need 3 independent equations to solve for 3 unknowns. Okay. So 2 independent equations, and the third one depends on the first 2. You won't get a set of 3 independent equations. Okay. We'll write and see, because you need to know this. Okay. We'll apply KVL to 1, 2, 3 and check, and you'll realize that you won't be able to solve. Okay. Let us do that. Seshank, you only tell me. Let's apply KVL to the upper small loop first. Where do you want to start from?
I'll start with the bottom left of
Bottom left of this loop. Okay. Fine. Let's call this as equation 1. So the equation 1 you are going to write would be, do you want to move clockwise or anti-clockwise?
If you move clockwise or anti-clockwise, you're moving the direction of a different current. So which current should we consider?
You have to consider both. So,
but if you move in the direction of I2, you're moving opposite to I3.
What did you say?
If you're moving in the direction of I2, then you'll be moving the opposite direction of I3. So
you can move what is there in that. It's not necessary that you should move in the same direction with every current. Okay. So your choice of whether you want to go clockwise or anti-clockwise is completely up to you. You don't even have to look at the currents.
I'll go clockwise.
Okay, you go clockwise. Fine. So we'll start this way. And the first element we come across is this 2 ohm resistor. So tell me how to write the potential change delta V across the 2 ohm resistor. The current in it is I3. Based on that, you tell.
Can I say minus 2 I2 or 2 I3? Which one is correct?
See, what is the law based on which you are finding out the potential difference across the resistor? Generally, forget about this circuit and all. Generally, how do you write delta V across a resistor?
In the direction of current, you say minus IR. Opposite, you say %.
What is I there? The current that passes through that resistor, not somewhere else. Okay.
Then plus 2 I3.
plus 2i3. Since you are going opposite to i3, it will be plus 2i3. Okay. Fine. Continue moving along that loop. You will come across the battery next. And you're going from negative terminal to positive terminal. How do you write the potential change across the battery?
Plus 10.
Plus 10. Negative to positive, potential should increase, so plus 10. Continue moving. You will be moving across the 1 ohm resistor. How do you write potential change across the 1 ohm resistor now?
Minus I2.
Minus I2, since you are moving in the direction of current and you have reached the starting point, so equal to 0. Fine. Next, for the lower small loop. Yes, you tell me, where shall we start from?
Bottom left,
Bottom left, clockwise or anti-clockwise?
clockwise.
Clockwise only want to go. Okay, no problem. So start moving along this loop. The first element you come across is this resistor. You're going opposite to I2. So how do you write the potential change across that resistor?
Sir, we are moving in the direction opposite to the current, right?
Yes.
So it will be I1, sir.
Where did I1 come from?
Sorry, I2, sir.
Plus 1 into I2. So simply I2. Okay. Continue moving along that loop. You're going from positive terminal to negative terminal of the battery. How do you write the potential change?
So we are going from the positive to negative, so it will be minus E, sir.
Minus
So
E,
it will
so
be
minus
minus
10. Good. Continue moving. The next element you come across is this 1 ohm resistor. And in that 1 ohm branch, you know how much current is flowing, you know which way it is flowing. So tell me, how will you take potential change?
So it will be minus 1, sir. Sorry, plus 1, sir.
Why?
Sir, because it is in the direction of the current I1, right?
In the direction of current, how do you write potential change across a resistor?
Yes.
How should we write? See, for the upper 1 ohm resistance, you were going opposite to the current I2. Then you took it as plus I2. Here, if you are going in the direction of current I1, then you should take minus.
Yes, sir.
So it will be minus I1. And then you come across this battery, 20 volt battery, from negative to positive. How do you write the potential change?
It is increasing, sir.
So plus 20 should be equal to 0. You have reached the starting point. Okay. Now let us consider the outermost loop. Seshank, you tell me, where shall we start from?
Top left corner clockwise.
Top left and clockwise you want to go. If you go clockwise, the first element you come across is this 2 ohm resistor. How do you write the potential change?
2I3.
Plus 2i3. Okay. Continue moving along that outermost loop. Then it is this 1 ohm resistor. How do you write the potential change?
Minus I1.
Minus I1. And then the battery from negative to positive?
Plus 20.
Plus 20. And you have come to the starting point. Okay, so this should be equal to 0. Now you add the first two equations. If you add the first two equations, you will see that I2 gets cancelled. 10 gets cancelled. You get 2i3 minus I1 plus 20 is equal to 0. This is what I was saying. The third equation you write will not be an independent equation. And using these three equations, you can't solve for I1, I2, and I3. You effectively got only two equations. You didn't get three. Okay. And the third one is useless. I mean, one of them is useless. Okay. So it looks like there are three loops here, but there are only two loops actually, two independent loops. The third one is the sum of the first two. Okay. So we need one more equation, and Anugraha, what you said is correct. But others also tell me, how else can we write equations involving current?
The junction rule.
You can see that there are some junctions in this circuit. So you have to apply the junction rule as well. At any one junction you apply, that will be enough. Let us take that green dot. At the green dot, that green dot junction, Harika, you tell me, First, tell me what is the junction rule?
So the current inflow should be equals to current outflow.
Inflow should be equal to outflow. At the green dot, what are the inflows of current?
So it will be I2
Hmm.
and yeah, I1, I2, and I3.
All three are flowing into that junction, right? So how do you
Yes.
write KCL equation?
So it will be I1 plus I2 plus I3 will be equals to 0.
Right. I1 plus I2 plus I3 is equal to 0. This is the third equation. And solving these three, you can find out I1, I2, and I3. Okay, solving part you do later. Have you learned matrices? Do you know how to solve equations using matrices?
No, sir.
Yes, sir.
No
Like
problem.
in maths,
Harika, what were you saying?
like in maths or like in physics.
Maths only. In physics, we won't teach matrices.
Yes, we learned it.
You learned.
Huh.
So you know how to solve 3 by 3 equations using matrices.
Yes, sir.
Okay, okay. If you know, it will be easy if you're comfortable with matrices. Otherwise, also it can be done. Seshank or Anugraha, you tell me, how do you solve equations?
You can add or subtract the first and second, second and third.
So you will eliminate the unknowns one by one. Like using the first two equations, like if you add them, I2 gets cancelled, you'll get an equation only in terms of I1 and I3. Or you can do something like this. Get I2 from the first equation, put it in the second and third equations. Okay. I'll just do it in this one case, just the equations I'll write. From the first equation, we can say that I2 is equal to 2I3 plus 10. So what I'll do, I'll use this value of I2 in the second and third equations. Then what does the second equation become? Second equation is I2 minus 10 and so on. No? So in place of I2, I'll write 2I3 plus 10. That is I2 minus 10 minus I1 plus 20 is equal to 0. That's the second equation now. And the third equation changes to I1 plus I2. In place of I2, I'll write 2I3 plus 10 plus I3 is equal to 0. Now you see these two equations. They're only in terms of I1 and I3. Two equations, two unknowns can be solved. Okay. You can maybe add them, I1 gets cancelled, or you take I1 from one of those equations and put it in the last equation. You'll have an equation entirely in terms of one unknown. You can solve. But this way it is slightly time taking. If if you're comfortable with using matrices to solve equations, it will be easy. Especially when there are three unknowns or more. For two unknowns, this method is better. You don't have to write matrices and all. That will be a time waste for two unknowns. For three or more unknowns, matrices method is better. Okay, anyway, solving and all you do later, but this is how we are going to apply KCL KVL to solve circuit problems. Okay, and remember, it may look like there are three loops here, but only two independent equations you can get. Third one has to be KCL. Okay. Next, try this question. Suppose there is a point here which is maintained at 20 volts. Let's say there is a resistance of some 5 ohms, then a battery of take 5 volts, then another resistance, okay, maybe another battery here, 10 volts. This resistance, let's take it as 10 ohm, and let's say this point is grounded. Calculate the current in this branch. There's only one branch here. By some means, we are maintaining 20 volt on one end, at one end. The other side is grounded, means the potential there is 0. Calculate the current in this branch. Anugraha, your answer is correct only. Others also solve it quickly. You can assume some current and you should apply KVL actually. But some of you may ask, like, where is the loop to apply KVL? Are you all able to see my screen?
Yes.
Okay, fine. There was a power cut here. Yeah, what I was saying is some of you may ask, like, where is the loop to apply KVL? You can create a loop. See, the potential at this point is 20. Here it is 0. So you can assume there is a battery of 20 volt between these 2 points. And then you get a loop. Okay. Actually, without that also you can solve, but this is one of the ways to do it. I got one answer as 1 ampere. I don't think 1 ampere is correct. Okay, Harika, tell me, how did you solve? Like,
So first, I took the current as I1
which way?
from 20 volts, sir.
It's to the right. You took current as
Ah.
I to the right. Okay. Fine.
So since I took the current as I, the 20V will be minus 20.
Why will you make it minus 20?
So because it's in the same direction.
No, I didn't understand. What is in the same direction as what, and why are you making it minus 20?
Like delta V1.
Delta V1. So you're talking about the potential change across something. Across what?
Across
Okay, continue. You'll write minus 20 is equal, and then?
and since I1 is flowing through the same the resistance also, I'll take it as minus IR.
Okay, so minus 5I1 you will write.
So, and similarly, in the 5 we'll take it as minus 5,
Okay, and then
and minus 10i,
minus 10I,
and finally minus 10.
and then minus 10. Why?
Sorry, it'll be plus 10. So
Okay, plus 10. And you equate this to?
equate it to 0. So
I didn't understand the logic behind this minus 20.
mhm.
Why should you take it as minus 20? Okay, anyway. Anugraha, tell me your idea.
Sir, it's the same thing, but it starts with plus 20.
Okay, but what is the concept here? Like, why are you writing it like that? That is what I want.
Concept behind what, sir?
I mean, who told you that you have to start like that and write like that? On what basis are you doing that?
The initial potential is 20 volts, so it
Okay,
would
the
start with
potential at the point where you are starting from is 20 volts. Okay. And then?
and then I assume the current to be flowing towards right.
Okay. Okay, fine. See, the idea here is generally for any quantity, change in the quantity is final value minus the initial value. Now we know how to write changes in potential across circuit elements. Okay, as you move from one side of the element to the other side, circuit elements or circuit components, whatever you want to call them, we know how to write potential changes when we go from one side to the other side. Okay. Now, generally for any quantity, change is final minus initial, and total change is nothing but sum of small changes. So sum of small changes is the final value of the quantity minus the initial value of the quantity. Now you send that minus initial to this side. So effectively what happens is initial plus the sum of changes becomes the final value. So initial voltage or initial potential, I should say, not voltage, initial potential plus the change in potential across the 5 ohm plus change in potential across the battery plus change in potential across the 10 ohm plus change in potential across the 10-volt battery, I'll call it as second battery, should be equal to the final voltage. Oh, sorry, final potential. This is the logic. Okay. And yeah, that is what we are going to do. Initial value, the point where we start from, like we are going to start from here and move to this point. Okay, there's no loop here. I didn't form the loop, so I won't call it KVL, but we know how to write potential changes. We are going to make use of that. So initial value here is 20, and across the 5 ohm resistor, it will be minus 5i. 5-volt battery, you're going from positive to negative, so minus 5. 10 ohm resistor, minus 10i. And 10-volt battery, you're going from negative to positive, so plus 10. And you have reached the final value, that is 0. That's all. So you get 30. Okay, 30 minus 5 is 25 is equal to 15i. And I becomes 25 by 15, that is 5 by 3 amperes. Okay, so this is the idea that we are using. Initial value, I mean, the initial potential where you start from plus the sum of potential changes should be equal to the final potential. Okay, Harika, Yash and all, is this clear?
Yes, sir.
And questions like this are very, very common in almost every exam. You'll find questions like this. Try another question. The capacitor has some charge on it. Then this resistance, let's take it as 2 ohms. Okay. And assume this point of the circuit is earthed. If you earth some point of a circuit, it means the potential there is 0. So we know potential at one point. The question is to calculate the potential at this point and also the current flowing in this circuit. Try this, all of you. Anugraha, your answer is correct only. Okay. Shashank, your answer is also correct. Okay. Harika, tell me, how are you trying to solve?
So first, I'm trying to apply KCL.
KCL. At which junction are you trying to apply KCL?
So like at the top right. So,
Top right is not even a junction. It is just this wire bent like this.
sorry, I mean KVL.
Okay, you want to write KVL for
Uh,
this loop. Where are you starting from?
at the top left.
Top left, and did you go clockwise, anti-clockwise?
I went towards the right. Yeah, clockwise.
Okay, clockwise. How will you write potential change across this capacitor first?
So it will be minus Q by C. So minus 6 by 2, it will be minus 3.
Okay, minus 3. Fine. Continue moving, you will come across this resistor. How will you write potential change across this resistor?
The potential change will be minus 2 into I.
Okay, current is going in the same direction, so minus 2I. Continue moving, then this battery, you're going from this side to this side. How do you write the potential change?
So it will be plus 10.
Plus 10. That's all. So how much is I?
So I will be
Okay.
it will be 7 by 2. So.
7 by 2 amperes. Okay.
Hmm.
Correct only. And how will you calculate the potential at that point that I marked?
So I want V equals to IR.
You want to use V is equal to IR. Tell me, what is V equal to IR, that statement called?
Current flowing through a certain resistance.
No, it's Ohm's law. Okay. You want to use V is equal to IR. In this formula, V is equal to IR, what does V mean?
The potential across the resistors.
Potential difference across the resistance. Okay. So tell me, how will you apply that?
So can't I use like 7 by 2 into 2 because it's flowing through that resistor?
Right hand side is 7 by 2 into 2. That's fine. What will you take as V?
V
itself.
10 minus 0.
You should take V minus 0. Fine. Okay, fine. So you can apply Ohm's law, right? You know potential at the right end of the resistor is 0. You need potential at the left end. So the difference in potential across this resistor is V itself. Okay, so you can directly write V is equal to 7 by 2 into 2. That becomes 7 volts. Okay. Actually, potential at that point you could have answered without finding out the current also. Because you know it is 0 here. Ground is at 0 potential. And when you move across this, it will become, the potential here becomes plus 10 volts because there's a battery between them. This potential is plus 10. Across this capacitor, the potential difference is 3 volt. When you go from this side to this side, you're going from positive to negative. So it has to decrease by 3 and become 7 volt here at this point. That way also you could have answered without calculating the current. Okay. Fine. So tomorrow or maybe day after, I'll send you a worksheet based on all this. You just have to apply KCL, KVL carefully. Okay? I'll send you a worksheet along with the answers. Or you take any book, any reference book, you'll find many questions circuit based. Okay. 1 loop, 2 loop, multiple loops will be there. Don't go to symmetric arrangement of resistors, infinite ladders and all yet. But simple circuits with 1 or 2 loops, you can apply KCL, KVL and find out the current. Okay, it requires a little bit of practice for you to become comfortable. Anugraha seems to be very comfortable with questions like this. Good. Okay, let us discuss series and parallel combination of resistors. We'll do this quickly because I'm sure you all must be comfortable with this already. And there's nothing special also. Simple stuff only. When do you say that a set of resistors are connected in series? How do you identify a series connection? Anyone?
Sir, when the end of a resistor is connected to head of the another one.
Okay. One end of a resistor connected to one end of the next resistor. Just resistors placed one next to another and so on in a single branch. You call that as a series combination of resistors. Fine. And the most important thing is that there should be no junctions in between connecting to any other element. Fine. You'll understand why there should be no junctions. We had discussed this point in capacitors also. Even for capacitors to be considered as series combination, capacitors should be placed in line, okay, one next to the other. They should all be in one branch itself without any junctions in between them. Can any of you recollect and tell me why there should be no junctions in case of capacitors? Like what happens if there's a junction?
Sir, is it like the currents will get divided?
See, in capacitors, we didn't talk about current. In this case, yes, the current will get distributed in different branches. In capacitors, why was it necessary that no junction is present between two capacitors?
So we talked about the isolation of
Good,
plates.
good. Isolated regions in the circuit. Isolated regions are supposed to be neutral. If there is a junction, for example, between two capacitors, usually when we take them as a series combination, we write charges like this, plus Q minus Q, and here we'll take plus Q. Because this isolated region is neutral, net charge is 0, it has to remain 0. Now, if there's a junction in between, there's no guarantee. I mean, this part is not isolated anymore. It's connected to something else. Then the net charge need not be 0. Then you cannot guarantee minus Q here and plus Q here. Okay. Then that series combination formula will become invalid. Okay. You'll understand why it has to be like that in resistors also. So let's say there are 3 resistors connected like this. Assume that combination of 3 resistors is connected to a battery. What we want to do is we want to replace this set of resistors with a single resistor which draws the same amount of current from the battery. Okay. Fine. Let's say the current here is I. Now, if there are no junctions between the resistors, whatever current flows through R1, the same current flows through R2 and the same current flows through R3 as well. All 3 of them will have the same current. Then the potential difference across the first resistor, delta V1, will be I into R1. And across the second resistor will be IR2. And the third one will be IR3. It's important that I is common in all of them. Okay. And now simply applying KVL, you'll write V minus IR1 minus IR2 minus IR3 is 0. Effectively, you'll get the current I as V divided by R1 plus R2 plus R3. That is the current that flows through this combination. Now what we want to do is we want to replace this combination with a single resistor which draws the same current when the same battery is connected to it. So let that single resistor be R effective. Let the voltage be V. In this case, we know the current is V divided by R effective. And we want these two to be equal. That's all. So 1 by R effective is 1 by R1 plus R2 plus R3. So you can just equate the denominators. You get R effective is equal to R1 plus R2 plus R3, so on, up to Rn. How many ever resistors are there in series? You can simply add all of them. In capacitors, when do you see a formula like this?
When they are in parallel.
When they are in parallel, correct. So this is valid when there are no junctions. So in case of resistors, if there are junctions between the resistors, there's no guarantee that all 3 will have the same current. What I mean to say is if there's a junction here The first resistor has a current I passing through it. Okay. The same current I will go here, but through that other wire, there may be another current getting added. Then the effective current, total current in the resistor R2 will be I plus I dash. Then you won't get an equation like this. Okay. Then you won't see that R1, R effective is R1 plus R2 plus R3. You can't replace them with a single resistor at all. So there must not be any junctions. Okay. So in series connection, current will be common. Through all the resistors. That's fine. If current is common, tell me what is the ratio of potential differences across the resistors? You look at the diagram and tell me directly what is the ratio of those potential differences.
Same as the resistance here.
IR1 is to IR2 is to IR3, I will get cancelled. It will be same as R1 is to R2 is to R3 and so on. If you know this ratio, you can directly tell what is the voltage across any one individual resistor also. Okay, without finding current, using this ratio itself, you can tell what is the voltage. Okay, so these are the only things you need to know about a series combination of resistors. Let's solve one basic question based on these. What is the potential difference across the 5 ohm resistance? Calculate potential difference across the 5 ohm resistance. Yes, your answer is correct only. How did you calculate? Did you use the ratio or did you find out current and then the potential difference?
No, sir, ratio.
Okay, fine. Okay, all your answers are correct only. It is 5 volt. So if you use a ratio should be R1 is to R2 is to R3. So you have to split the voltage in the ratio 6 is to 5 is to 9. 6, 5, 9 become 20 parts. Out of 20 parts, the middle one will get 5 out of those 20. So 5 out of 20 into 20 becomes 5 volts. Okay. Easy question. Without finding out the current also, you can tell what is the potential difference across any one resistor in series. Okay. Let's quickly discuss parallel combination also. Can one of you quickly tell me how do you identify a parallel connection of resistors?
If their ends are connected.
Right. Left hand and left hand should be connected. Right hand and right hand should also be connected. Then you call it a parallel combination. You can take any number of such resistors. Assume they are all connected to a battery. Okay. Since they all have their left ends in common, all the left ends will be at the same potential, and it doesn't matter if there are junctions or not also, because the wire is a conductor. The entire conductor will be at one potential itself. Okay. And right ends are connected, all the right ends will be at one potential. And if all left ends are at one potential and all right ends are at one potential, the potential difference across all three of them will be the same. And you can see that the positive terminal of the battery is connected to the left side and the negative terminal is connected to the right side. So whatever is the voltage across the battery, the same will be the voltage across the resistors. So all three will have V, V and V itself. Okay. Now we know the voltage across each resistance. We should be able to tell the current. Then current in this resistor, we know V is equal to IR, so I is equal to V divided by R1. That's the current in this branch. Here it will be V divided by R2. And in this branch, it will be V divided by R3. All these currents should be coming from the battery itself. Okay, it comes like this. And some part diverts this way, some current diverts this way, and some current diverts this way. Or you apply KCL at any one junction also. So let the total current be I. You can say that the current I is the sum of currents in the three branches. So V into 1 by R1 plus 1 by R2 plus 1 by R3. And if you want a single resistor to do the same, to draw this much current, let the resistor be R effective. Same battery of voltage V is connected to it. And it has to, we want it to draw the same current. The current it draws here will be I is equal to V divided by R effective. So you can write it as V multiplied with 1 by R effective. And we want the currents drawn in both cases to be same. So therefore you get 1 by R effective for a parallel combination is 1 by R1 plus 1 by R2, so on, 1 by Rn. Okay, quickly tell me, what will be common to resistors connected in parallel?
Potential difference.
Potential difference, correct. So all three will have the same potential difference, that's fine. Potential differences are same. What about currents? Should they be same?
No,
No.
sir.
Not necessary. What is the ratio of currents through the resistors?
Inverse ratio of the resistance.
Inverse ratio of the resistances, correct. Therefore, I1 is to I2 is to I3 and so on will be 1 by R1 is to 1 by R3 and so on. Voltages or potential differences will be same across all the resistors, correct. And it doesn't matter if there are any junctions also. Potentials will anyway be common. Okay. Now see, in a series combination of resistors, the effective resistance is R1 plus R2 so on up to Rn. So if you connect resistors in series, will you be increasing the resistance or decreasing the resistance?
Increasing.
Obviously, the resistances are getting added, no? So it will add up, the resistances will add up, and the total resistance or the effective resistance, R effective, will be greater than any of the given resistances. Right. And what about parallel combination? What do you think, or how do you think the R effective will be related to the individual resistances? Will it be greater than all of them or less than any of them, or you can't say?
Less than all of them.
It will be less than any of the given resistance, correct. So R effective in parallel will be less than any of the given resistors. So if you want to decrease the resistance of a circuit, you can connect some extra resistors in parallel. the overall resistance will come down, and the overall resistance will be less than any of the resistances that you connect in parallel. Okay. Okay. Let's solve one question. Okay, tell me this quickly. If there are only two resistors R1, R2 in parallel, how will you find out effective resistance? Harika, you tell. Only two resistors R1, R2 in parallel. How to find
So
out
it will
effect?
be
Huh.
R1 plus R2 by R1, R2.
No.
Resistance in parallel rates.
Two resistors in parallel. I am asking effective resistance.
So it will be 1 by R1 plus 1 by R2.
What is 1 by R plus 1 by R1 plus 1 by R2?
The resistances of the
You are saying 1
the
by R1 plus 1 by R2. What is this?
will be the effective resistance.
So you are saying R effective is equal to 1 by R1 plus 1 by R2.
Yes.
No. That will be dimensionally wrong. Don't you think so? Because left hand side R is in the numerator, right hand side R values are in the denominator, 1 by ohm, 1 by ohm. How will the dimensions match? See, this is a very common mistake that students make. You know 1 by R1 plus 1 by R2, but you should remember that it gives you 1 by R effective. It doesn't give you R effective. Harika, got it?
Yes, sir.
So how much does this become? It becomes R1, R2, and numerator will be R1 plus R2. But this is not the effective resistance. Effective resistance will be inverse of this. So R1, R2 by R1 plus R2. For two resistors, you can use this formula to directly tell the effective resistance. If there are more than two, you write it this way and find out 1 by R1 plus 1 by R2 and so on. Okay. So you're given a circuit here, simple one only. Find out voltage across each of the given resistors. Okay, Anugraha, your answer is correct. How did you do it so fast? I mean,
I'm using the usual method. Effective resistance, current, and then voltage across each resistor.
okay, you first found out the effective current, then okay, effective resistance, then current, and you distributed the current. Okay, not an issue. You can do that. Fine, but since you have time now, you try to do it using that distribution of voltage method also. You know in what ratio it gets distributed, no? Finding out effective resistance, it is also a good method only, but try to do it the other way. Harika, how are you trying to solve?
So first I found the overall current that will be 1 ampere, and then I'm trying
Okay.
to do V equals to IR and find it.
Okay, fine. Overall resistance will be 10 ohms and current will be 1 ampere, correct? That 1 ampere current will flow like this in the main branch connected to the battery. There's only one battery, so it flows like this. Reaches this junction. At that junction, it has to split into two parts. Some current goes this way and some current goes this way. Here it is 1 amp. Okay. And 9, 3 are in series, it becomes 12. 12, 12 are in parallel. If two resistors are in parallel, they'll have equal currents passing through them because we know ratio of currents when resistors are in parallel is 1 by R1 is to 1 by R2. 1 by 12, 1 by 12, it's like 1 is to 1. So half current will go this way, 0.5 amperes. Half current will go this way, 0.5 amperes. Then you can tell the voltage across any resistor. Fine. Okay. You can use the ratio also without taking this current. I mean, without finding effective resistance and all, you can directly use the ratio. How to do that? See, what are connected to the battery? On one side, this 4 ohm is there. On the other side, this combination is there. 9, 3 become 12. 12, 12 become 6. So 4 and 6 are in series. They are connected to the 10 volt battery. If two resistors are connected in series to a battery, then the potential gets distributed in the ratio of resistances, 4:6. So this will get 4 volts and this combination will get 6 volts. So across the 12 ohm resistance, it is 6 volt. Across 9 and 3 combined, it is 6. And that we can again split in the ratio 1 by 9 is to 1 by 3. That's like 3:1. Wait, 1 by 9 is to 1 by 3. Multiply 1:3. 1:3. So here you will get 1:3 means 4 parts. 1/4 of 6 volts. And here you will get 3/4 of 6 volts. That way also you could have distributed the voltages. Okay, so we'll stop this class here. What we have discussed today is some application of KCL KVL in one or two circuits, then series and parallel combination of resistors. Fine. Next class will be on Tuesday itself. And in that class, we will discuss some complicated networks of resistors. And if possible, we'll discuss Wheatstone bridge also. Okay. After that, we have to discuss cells connected in series, in parallel, then potentiometer, and that's all. That will be it for this chapter. Okay. So tell me, do you want me to send questions based on circuits, or do you have books from which you can solve questions? If any of you want me to send, I can send, but you can easily find circuit questions in any book, they'll be there. So I just want to know if you have those reference books or not.
Sir, HC Burma.
In HC Verma, the number of questions will be less. Concept will be tested thoroughly, but number of questions will be less. Did you not buy that Pearson book that I suggested?
Not yet, sir.
See, to get a good grip on the concept, no, you need to solve some 10 to 15 questions on that concept itself. So suppose you want to become thorough with KVL, minimum 15 questions based on KVL only you have to solve. For that purpose, I suggest that book. Okay. Other books also will have question. Maybe your module has question. Anyway, I'll send the worksheet. Don't worry. So KCL KVL series parallel connections of resistors. Fine. I'll try to send it
So
tomorrow. Huh.
the Pearson book, like there will be one book for one chapter, right?
No, there'll be one book for 11th class, one book for 12th class.
No, sir,
Yeah.
I went through Amazon, so there were like different books for different chapters.
No. Pearson Physics for, or Pearson JEE Mains Physics. That is the name of the book. You'll have volume 1, volume 2. That's all. Volume 1 is for 11th class, volume 2 is for 12th class.
Sure, sir.
Okay. You search once. If you still don't find, you let me know. I'll send you the links.
Yes.
Anyway, I'll send the worksheet. Don't worry. So, okay, we'll continue on Tuesday. Thank you all.
Thank you, sir.